Welcome to this presentation all about thermal profiling. We will cover today why thermal profiling is currently underused in bakeries and also what can be done to start collecting reliable data as of today. So I'm Stefan Fjelldal. I work for Falk Thermal and I have been about 27 years in this industry now. 2/3 of this time working for Eastbolt Bakery, which is now Bimbo QSR, and the last third on myself and also involved in this thermal profiling process. Today, we're going to go through 4 points, 4 sections, starting with the introduction to thermal profiling. It's a little bit actually more than introduction. And the second part of this process will be to go through the different barriers that are avoiding us to adapt thermal profiling, which brings us to the third part where I can explain how to remove those barriers to usage of thermal profiling. And finally, how to maximize the data that we're getting from thermal profiling and what the future perspectives are, knowing that there's a lot of things going on in this field currently. So let's start with the section 1, introduction. The definition is quite simple, actually. It's basically to collect data from a product during its baking stage. And I would actually add that it's not only the baking stage, could be done at any stage that involve thermal processes. On this slide, I have depicted a hamburger bun, which is my area of expertise, but this also shows in the symbolic shape of a bun in the middle of the slide. However, any shape of bun could be applicable to this presentation. You could show a loaf or a baguette. It would also be applicable. One thing that I also wanted to mention is that if you want to monitor how your oven is behaving, then you need to put sensors in the oven. If you want to monitor how your product is behaving when it's going through the oven, then you need to put sensors inside the product itself. And this is what's going to happen throughout this presentation. I will always talk about thermal profiling with probes being inside the product. And those two big red arrows are also showing some kind of complication when dealing with thermal profiling. It's not that easy because we have a gradient of temperatures. It's not a uniform temperature inside the product throughout the baking process, which makes it a little bit tricky sometimes to collect the data. We will see that later. Small introduction about the different heats. The heat is entering the product in 3 different ways, and usually it's a lot of convection, which is basically blowing hot air on the product. You can also have radiation. This is the heat that comes from the inner walls of the oven. They are getting hot and they will emit the heat to the product. And also conduction. Your product is laying on a baking pan, a baking tray, or the conveyor itself. And therefore, we also conduct some heat towards the product. So there are ways to segregate, to differentiate those kind of heats and how they enter the product. However, it's quite complicated, and the good thing is that whatever heat that you have in your oven, as soon as it hits the surface of the product, it becomes Celsius or Fahrenheit, which can quite easily be picked up with a thermometer. Of course, there are some constraints with doing this inside an oven, but it all comes down to temperatures. I have shown here a typical result, a typical graph that you get from thermal profiling. Usually it's 2 curves, 2 charts, one corresponding to the ambient temperature of the oven, which is the higher chart in dark red, and the just underneath what is called the S-curve. And by definition or by convention, the S-curve is the temperature of the product from the core of it. So it's in the middle of the product, and this is what produces the S-curve throughout the baking time. And while the ambient temperature, there's not much information to gather from this, it allows the system to detect when it's entering the oven and when it's discharging from the oven. So it gives us some indication. But most of the valuable information is really coming from the S-curve when it's taking from the core of the product. Now let's go one step deeper into the analysis of those curves, especially the S-curve. The S-curve here is cut in three sections, three phases, which corresponds to each baking phase. And you can see that each phase corresponds to a particular section. You have the flat part of the S-curve, which is phase 1, and then a steep incline, which is the phase 2, and finally it's a plateau on phase 3, which is called the bake-out. The phase 1, which is the entry of the oven, we call it the oven spring for one good reason. This is where your product is still gaining a lot of volume. It's actually like an extension of your fermentation time because the yeast is still alive in this area. Then you're entering the phase 2, and phase 2 is more or less where your wet dough is becoming crumb. And there's a lot of transformations that are happening inside this area. You have the proteins that are denaturing, you have the starch that is gelatinizing, the CO2 is leaving the water is becoming vapor. There's tens of transformations that are taking place in this area. And finally, the phase out, the bake out, which is corresponding to mostly the finalization of the bake and including the coloration. This is where your product is getting color through the Maillard process mostly. So you might ask, what separates phase 1 to phase 2 and phase 2 to phase 3? Well, this is another convention that are being used in bakeries. It's called the first transition, which is between phase 1 and phase 2, is called the yeast kill. And it's happening at 60 degrees C, 140 degrees Fahrenheit. And basically, it's the stage where the yeast is dying out, it's fading out. And this is done at 60 degrees C in most bakeries. Unfortunately, there's not a standardization throughout the bakeries. So it needs to be, in case you're comparing apples to apples, you need to make sure that everybody's on the same page and using the 60 degrees C or 140 degrees Fahrenheit. The next transition from phase 2 to phase 3 is called the arrival at 93 degrees C, 200 degrees Fahrenheit. And at this stage, the crumb is set and we are entering the phase where you're baking out and doing the coloration. So again, make sure that if you compare your data to other data, that we're speaking about the same yeast kill and arrival values. Now we can go even deeper. Now that we have segregated the baking in 3 phases, of course, they can be measured. We can extract metrics from it. And here, of course, for each phase, we can measure the time in those phases that could be converted to percentages of total baking time. So this allows you to, for instance, compare one run to another run. Quite easy. But if you look even deeper on this S-curve, it's depicted here with the green arrow. This green arrow actually shows you the temperature at which your product is entering the oven. So, which indirectly gives you a hint of the temperature of your proofing process, the fermentation, and which is also very valuable and has a lot of influence on the baking curves. And the red arrow that you see at the end of the S-curve, which gives you the temperature at which the product is discharging from the oven and is always underneath 100 degrees Celsius because it doesn't exceed the boiling temperature. And it also gives you some kind of indication of how much moisture you still have in your product. The higher the exit temperature is, the less moisture you have. So this could be also used for the cooling process. And finally, in the middle, you can measure the phase 2, but you can also have fun measuring the heating rate, see how much temperature is increasing this short period of time. It is said by some bakers that the stalling rate of your product is linked somehow to the heating rate. So which means that if you measure the heating rate, maybe you can predict the stalling rate. One more thing about thermal profiling, because it's the only tool currently used for food safety assessment. Food safety assessment was reinforced in 2011 by Barack Obama with the Food Safety Modernization Act for the bakeries in the US that are concerned about this. And it basically is to assess the safety factor. And in our case, bakeries, we are lucky because heat is our friend, because heat is the enemy of the pathogens such as Salmonella or E. coli. So if we measure the temperature in the core, we can know the exposure and calculate quite easily how dangerous our product is. And what I wanted to say here is that we have gradient of temperatures. The temperature is entering from the outside to the inside. So of course, the potential pathogens will tend to survive longer in the middle than on the outside of the product, which means that to be really safe, you need to collect the data really from the core, which is where it's basically the worst case scenario. Okay, section 3, we will cover now how to remove those two barriers that were discussed earlier. The first barrier being the unreliable data. And how can we know that data is unreliable? Well, if you do the same thermal run twice in a row in the same conditions, the same operator, same product, same material, you should expect the same results. And if you do not get the same results, then basically it's unreliable data. And what I see very often is that the position of the probe is not under control. And I think this is quite an important aspect for to monitor the position of the probes. Here's an example of a solution that will not yield good results. You see loose wires. The temperature is being read at the tip of each of those loose wires, and they are hand-fed into the product, the core of the product. And when it's done by hand, it's really hard to know if you're reaching really the middle of the product. And even worse, even the weight of the wire itself will make the probe tip move during the baking phase. So this is actually not generating a huge amount of reliable data, and especially not comparable data. The second barrier for thermal profiling is the knowledge. If you are given the chart of a baking curve and you are asked to analyze this, you will end up saying that it's not easy to know if it's a good or a bad bake. And but there is a very efficient trick to help analyze the data, and it's basically to benchmark. When you benchmark, you are comparing. So it means that the data needs to be repeatable and reliable. But if that's the case, you can do a benchmark, which is, okay, let's do 2 runs and change something in between the runs and see how it's reflecting on the curves. And there's no need to be a scientist or a technologist to do this. It's really where your team will pick up knowledge, because they would change one setting on the oven, for instance, and immediately see the impact on the curves. And as an example, you can see here 2 baking curves, one in red and one in blue with the big arrows. Those were done in the same bakery, the same day, the same product. Everything was the same, and we still have a big difference in the graphs here in the charts. And there was actually one change that I did not yet mention, which is that the curve with the red color was done on an empty oven. Sometimes continuous ovens, they do run empty when you have a changeover or a breakdown. And when the new product is entering this empty oven, well, then you have different conditions. And this is showing up in this charts. And so this tells me that this bakery probably needs to make some adjustment to the oven when it's running empty. And it also shows up in the metrics. The metrics are circled here, 43% and 50%, which corresponds to the yeast kill time. So, which means that in one case, we're reaching 60 degree C internally after 43% of the baking time instead of 50. So there's a huge difference here. And again, this is how we can do benchmark by just changing one parameter and then comparing before and after. This could be done with a new ingredient. In our case of bakeries, with a new crop, a new set of pans, for instance. This brings us to the last part of this presentation. What can be done with the data and what can we expect in the future in terms of thermal profiling? When we look at bakeries, we have data from all over the bakery, from each of the steps. We also have the information from outside the bakery. The mill is providing you with analysis of the flour. And we have this data overall, but as we have seen in this presentation, I only covered the baking phase with thermal profiling, which is one of the yellow bubbles here, but it would be equally adapted to for proofing process and also the cooling process, which makes sense because those three processes are the ones that are the most time consuming. That's where your product is staying the longest in the bakeries. So it makes sense to have better control of what's really happening here. And again, when you look at the data, well, you have a lot of data, but not necessarily from the product itself. You have data from the product in the beginning, from the flour, from the makeup. At the end, during the packaging, you know the weight, you know the color, but you don't have product from the data itself during the proof, the bake, and the cooling time, which is what basically is covered by thermal profiling, as you can get data from the product. Of course, it's an intrusive operation to put probes into the product, and it needs to be made as easy as possible to gather a lot of information. But when you have it, it can really yield big results. And of course, if all this data could be combined into one location, there are many systems now that collect and that analyze that. And if we also apply some of the modern tools that we all speak about since for the last year or 2 years, which are basically handling the data in a big data way, artificial intelligence, machine learning, those are the tools that can be easily be implemented if all the data is in one location. Now, future perspective in terms of sensor technology. Of course, so far I've only spoken about temperature, but we could quite easily add some other dimensions to our thermal profiling. And one way would be vibrations. Your product is exposed to vibrations throughout the baking, and it could be measured quite easily and maybe also optimized. Maybe some vibrations are detrimental, but maybe some vibrations are actually improving maybe the fermentation. Who knows? If we don't measure it, it will be hard to know. There's also technologies to measure the gelatinization of starch, to know exactly what temperature starch is transforming, which can also be another dimension added to thermal profiling. And why not video? And not only video that analyze the color and the shapes. There are some nice algorithms that go much deeper than probably can open up unprecedented resources in this area. So this is a very quick overview of thermal profiling. I hope it gives you some insights of what can be done in your bakery and what can be done in the future. And I'm very happy to share this knowledge with the Bakery Live audience out there. Thank you so much.
Stefan, thank you very much for joining us at Bakery Live. That was a very interesting session. I did want to ask you a few questions, and just to start off with, how much human intervention is required during the thermal profiling process, or is the entire process, carried out through automation?
Thank you for the question and for the invitation for this Bakery Live session. Thermal profiling is currently taking up extra resources. It's not something that is automatic. Usually it's an equipment that is installed manually prior to the oven and removed manually after the oven. So it's a voluntary act. It's intrusive as well. So we need to take product out of the flow, put in the sensors in the correct way, and then put the products back into the flow again. So usually it's the line supervisors or QA persons that are doing this on a regular basis. Could be several times a week or a month, but it's not a continuous process. It's a batch process indeed.
And do you think that this might be something that could change over time, over the next coming years, that it could become something that is less reliant on human intervention?
I think indeed it needs the level, the barrier of entry needs to be lowered to make it easier to use. Currently, it's quite bulky equipment because it needs to be protected from the heat. So what I'm seeing now is that the solutions are made easier and easier to use. But it's still not automatic. It will be quite hard to make a fully automatic solution because it's intrusive. You need to put sensors into the product, so which means that it could be simplified, but not fully automated at this stage, not with the current technologies, in my opinion.
And you mentioned the benefits. I think they were quite clear. You know, the fact that bakers can make the best goods with the best texture and the best taste through thermal profiling, and also there's a food safety element involved as well. So I wanted to move into actually possibly the challenges that might arise. What would you say are or is the main challenge when it comes to the mass production of baked goods and thermal profiling during the mass production?
It's most bakeries want to have uniform products, and so far ovens or any thermal process is basically a black box. So we don't know what's happening, not know much about what's happening inside the proofer, the oven, or even the cooling process. And gathering this data can allow the bakers to fine-tune the baking, maybe limit the overbaking, which is probably one of the challenges we have today in terms of energy efficiency as well. And of course, when you have numbers, it makes it easy also to make changes. If you remember the S curve, which comes in 3 parts, you can adjust the oven to shorten down or lengthening some of those phases just by playing on the oven. So this is where you can actually only by the fact that you have data, then you can start to play with this data and maybe see how your oven or any process is interacting with it. And from there on, the data, thermal profiling doesn't tell you if the bake is good or bad, but it gives you values. Then you have to make a human assessment if it's good value, good quality or not. But at least you have the values, which means that you can go back to those values in case you are moving away from them.
And when it comes to that data, you mentioned as well that it can be unreliable. What do you think needs to happen moving forwards to make that data much more reliable?
Well, the electronics are very reliable when you only look at the electronics. The probes are also very accurate and reliable. But the main point of unreliability is coming from the position of the sensor. And if you are off by just 5 millimeter inside the product, it can yield up to 5 degrees C offset or a 5-degree error. So it's a huge amount of error, especially if we're speaking about food safety, because that's going to be, it's going to give you wrong values, wrong data. So I think that the biggest work is going to be carried out on the positioning of the probes to make sure that the probes are always in the right position, which will yield repeatable data. And when it's repeatable, you can compare it from one bakery to another. It somehow becomes a standard if you know that the data is really being sourced at the same place each time. So there's not a one solution because there's many types of products, of shapes of products. You have baguette, you have loaves, you have buns, you have And I believe that it's going to specialize. So the solutions will be specialized for each product. So that we're really sure that the probes are positioned in the right place.
And just to finish with your future predictions in terms of the innovations that you mentioned, how do you foresee solutions like, for example, video and vibration sensors progressing over the coming years?
Yes, this is an interesting area indeed. Right now we're looking at the easy metrics, which are our temperatures. Those are quite easy to collect. And so far, I've seen a few applications where data is used as well, but video data, sorry. But I guess that video can, there's a lot of data that can be taken from video if you start to dig deep into it. And not even mentioning about hyper spectral, which means that you look into areas that the naked eye cannot see. And they could maybe opening up some new areas of expertise during the baking phase to see how the moist is leaving the product at one stage. Then maybe this can be visualized throughout the video. Actually, you spoke about vibration. This could also be measured with video. If you amplify the movements, the small movements that you see in the video stream, you can actually measure also the vibrations. So there's a lot of information that could be collected. It's only a matter of knowing if it's valuable to the baker or not. There's no limit otherwise.
Well, it sounds quite exciting. I think it's interesting. It will be interesting to see how these innovations do develop over the coming years. Yeah. Thank you very much once again, Stefan, for joining us.
Thank you so much for the invitation to join this presentation. Thank you very much.